In this video, we're going to go over the data structure called linked lists. So linked lists are something different than what we've talked about before. So the linked lists are going to be a linear data structure. We'll start with our old friend, the memory map here. Okay. And the way this works is that you'll basically place what we'll call a node. Okay, so the linked list is going to be composed of nodes. Okay. So you'll place a node in memory, that is N-O-D-E-S. Okay, place a node in memory. You'll store something there, okay? And then you'll also store a pointer to the next memory location, okay? So they're scattered out throughout the available memory. Okay, so again, these are dynamic data structures, so they're going to be in the heap, okay? So it's important that you have access to the first node, okay, which is either called root. This will be a pointer, a root pointer, or sometimes it's called head. They're interchangeable, okay? And we're going to keep that because there's no way to get to say this is your third element here. So if you want to get to the 25, there's no way to get here directly, okay? Unless you can always create pointers to everywhere, but if you create pointers to everywhere, then you've defeated the purpose of a linked list, okay? So basically with a linked list, you go to root, and then you go root knows how to get, so this node knows how to get to this node, which knows how to get to that node, and then it knows that it's done, okay? So it allows for pretty efficient storage. There's not a lot of overhead. There's no random access. It's all sequential access, okay? And if you lose the root, you in essence have lost the entire linked list. Note that you haven't freed the memory necessarily, although the garbage collection is now a feature of C++ in ways that it was not before, okay? So let's first talk about how we're going to create this node, the question of a node, okay? And there are a couple of ways you can do this. You could do a class for the node, and sometimes books and different instructions will do that, but I really think that's overkill. Okay, so the way we're going to approach this is to use a struct. Not sure if you've seen structs or not before, okay? But a struct is basically a class without any functions, okay? So it's just the member data, okay? In fact, structs are a part of C, which is a non-object-oriented language, okay? So for an object-oriented language, you have to have classes which have the member data and then the functions that act on them. The struct is just a way to have you're creating a new data type out of existing data types, okay? So on our node, we only have to have two things. We have to have an info, okay? And this can either be typed through a templated function, or for this example, we'll call it an int. Could be a string, could be a float, could be a Boolean, whatever it is, okay? So we're also, the next thing we're gonna have is going to be a pointer to a node. I'll actually put this, remember that asterisk can go anywhere. This is called variably either link or next, depending on your implementation, okay? We keep talking about ritual in this class. I need to stick with info and link, but sometimes I'll fall back into data and next, which is kind of the other things people use, okay? But don't follow me, my example, pick one and use it, okay? So we're gonna try to use info and link, okay? Note, if you needed to store other things there, traditionally there's only one element in a linked list. There's nothing to say you can't put two elements. If you wanted to put a linked list of names, you wanted a first name, last name, that's perfectly okay, okay? If you go too crazy on that, then you probably need a different data structure, okay? So, so that gets us started on that, okay? And then what we're going to do here, we're going to create a class. I'm going to do this in more detail in the terminal window, but for right now, we can go ahead and get ourselves started. Okay, linked list, and in the private section, what we're going to have is going to be a pointer to a node called root, okay? That's all we're going to have to store, okay? That will point to, again, the first node in memory, okay? And then the public section will have various things. Note that I normally do the accessors and mutators, the other and the constructors and destructors. That doesn't really necessarily follow in a data structure like this. Okay, so I'm going to kind of not do that, but we will need to have a constructor, and we'll go ahead and show this one here. Then we're going to get to some examples of how other things may work. Okay, so the constructor is pretty straightforward. Okay, again, there's no return type on a constructor, so it's just linked list. In this case, takes no parameters. All it does is set root equal to null. Okay, and I assume that you've seen null somewhere before, but null is self-aware nothing, if that makes sense. So it's not, it's saying there is no memory address. It's not just lack of a memory address, it's consciously nothing, okay? Which I know is very philosophical, but that's kind of the idea, okay? So we have to have the constructor to get this started, which will create the root, which is all that we really have to worry about, okay? So then when we create a new linked list, okay, so if we were, say, down in our int main, I'm not gonna put the whole code here, but you get the idea. If we were to say linked list LL, for example, I know LLs are difficult because they look like ones, but let's just go with it. That would just set a root pointer to null when we first get it started, okay? And then we can kind of do stuff from there, okay? So let's look, there are a couple of ways you can draw linked lists. A lot of times people will draw them this way, where you have the data over here. So you've got a 5 here, and then you'll have a pointer from here to the next node, okay? Note that these are not contiguous in memory. I mean, I guess they could be. They're not guaranteed to be contiguous. They're going to use what memory is available, okay? And then they'll use that kind of a nomenclature to be at the end. I tend to prefer this way, okay? So this is our first node, okay? And the bottom section points to our second node. And this becomes a pointer. And then if we have a third node, it points there, okay? And then for the last, we just put a backslash to show null, okay? Either of these is fine, okay? So again, when we start off, we have root that points to nothing, okay? So our first task is going to be to insert a new node, okay? And I'm not going to work through the code. We'll do the code in a minute. I want to talk about the ideas here, okay? So you have root pointing to nothing. So the steps here we're going to have, okay? We're going to have to first, we're going to have to create a new node. Okay. So at this point with root pointing to null, you have not allocated any memory. Okay, so we have to create a new node. Okay, we're going to have to add whatever info we're going to store. Okay, and then we're going to point our root pointer to this new node. Okay, so that's the basic idea how this is going to work. Okay, so we start off, we have root that just points to nothing. Okay, we're going to create a new node. We can call it new node if you want. Okay, when it's created, through our insert function. So again, we're working on the insert. We're looking at an insert at tail, basically. We're going to insert at the end. Okay. So if it's empty, it's pretty straightforward, right? Whatever data we're sending in, say we're inserting a 5 at tail. Okay. So it's just going to insert the 5 as the info. So new node. That's the an element of node, so it's a struct. So I can just say new node info is equal to 5. It's the data we're passing in. Okay. And then I can set new node link to null. So we have that node. Okay. Then I can just say root is equal to new node. And now the root pointer will now point to here. Okay. So that's the idea. Okay, new node's a pointer as well. Yeah, I'm sorry, I didn't say that. You're creating a pointer, you're not creating a new node, you're creating a pointer to a new node and allocating the memory for it. So that's a dynamic variable. Okay, then you're putting up to that. At that point, you can delete the new node if you want, because you don't care anymore. Okay, so that's if you insert to an empty list. But if you have an existing list, okay, so let's say we're there and we have to insert 15, let's say. Okay, so with this, when it's not an empty list, so you can check to see if root is equal to null, then you know it's empty. Okay, if not, we're going to have to search to get the last node. Okay, so if you look back here, how do we know it's the last node? We know it's the last node because its link is equal to null. Okay, so we're going to have to traverse the list to see if we're at the end. Okay, so we can do that by setting a temp pointer that points to root. Okay, then we ask the question, is temp link equal to null? If it is, we're at the last node. Okay, so we can just add a new link. Okay, so again, we're going to create a new node. We're going to put the 15 there. We're going to put the null there. Okay, temp still points to this node over here, so I can just say temp link is going to be equal to new node. So that replaces that with that. And now we've added that to our list. Okay. So a similar process, let's go ahead and add another one. If it's that was just with a 2 one. So again, we're going to add a 25. Okay. So again, we set a temp here. We can go ahead and create the new node first. It doesn't matter. It's out there somewhere in space. It's got that. Okay. Our temp, can make this in red. It starts off here and it's going to say, does temp link equal null? If not, okay, so in our case, we're not, we'll let temp be equal to temp link. By doing that, you're moving temp to here. Okay. Now, if you say, does temp link equal to null? It does. Okay. So we go ahead and change that to that, and we've added toward the end. Okay. And you can just keep doing that every time you're adding. Okay. Note that there are other additions that you can do. Okay. You can insert at the beginning. Okay. So let's take a look at that. If we want to insert at the beginning. So let's say we have, again, a 5. We already have there. We have a 15. And we have a 25. That points to there. That points to there. We have root pointing here. Okay. So in this case, we want to add a new one before root, or before the first element. Okay. So if this is 1, that's 2, that's 3. So we add one before 1. Okay. So that's adding at the front. Okay. So to do that, we're going to create our new node as always. Okay. And let's say it's got a 0. Okay. And it will point to there. Okay. And now we have to reroute things. Okay. So we have to reroute things without losing them. We don't want to lose the root. We don't want to lose the new node. Okay. So if I start by routing the new node link, which is here, okay, I'm going to route this to root. Okay. So now I can get from, again, new node is a pointer that points there. So new node link points to root. Okay. Now I can point root back to new node link. Okay. And that's going to insert it at the beginning. Okay. So we can insert from the beginning, we can insert from the end. Okay. You may also want to insert in the middle. Okay. So let's look at what that would look like. Okay. You'd have to have a way to tell where you want to insert it. Okay, so there have to be some kind of positioning or look for something, or you can do an ordered linked list or whatever. Let's say I want to insert 10 and I want to insert it between 5 and 15. Okay, so it's currently equal to a null. Okay, this is so new node points here. Okay, so in this case, again, I'm gonna have to use the temp to get it to the one that I want to find. Okay, and you have to specify that in some way. So temp points there. Okay, so what I have to do first, again, I have to get the new node set. If I would just set temp link equal to new node, okay, then this goes away, this points here, and we've lost the rest of the list. Okay, so I have to start like we did before by replacing the new node next to temp link. Sorry, not did next again. The new node, so new node link is going to be equal to temp link. Okay, that points that there. Root still where it needs to be. Temp still where it needs to be. Okay, and now I can point temp link. Okay, so temp's pointing here. Temp link will be equal to our new node. So it's going to go there. That's how we can insert in the middle. Okay. When you're going through the homework and going through problems with this, I think it makes a whole lot of sense through these kind of diagrams, just so you can kind of see what's going on. Okay. So the next thing we can do here, if we want to do a delete, the delete is going to have another component we can talk about here. And again, I'm not doing code here. I'm just doing the ideas. If you don't understand it, you're not going to be able to do anything else. Okay, so we have root always points to the first one. We have that, we have that, we have that. Okay. So to delete something, okay, it's possible you may want to delete the head or delete the tail, and you can certainly do that. But normally we want to delete some item. So let's say we want to delete, let's say 15. Okay. So in order to do that, we're going to have a search function, right? So let's talk about search first. Okay. So if we're going to search, okay, to search for something, we're going to have to set some kind of a pointer. Let's just go to C for current instead of temp. It doesn't really matter. Okay. And then while I'm pointing here, I can see if C info is equal to whatever key I'm searching for. Okay. If it does, then I'm done, right? I'm good. Okay. But if not, I can let C link, or no, sorry, C equals C link. And I can just keep moving down that way. Okay. So this allows me to find, let's say I want to delete the 15. Okay. So that's not correct. This is now correct. Okay. So to delete this, I'm going to need to route from this node over to that node. Okay. But there's a problem. The problem being we don't have any access for this node. There's no way to get there. Okay. So in this case, we're going to have to maintain another pointer, a P or previous node. Sometimes these are called current and previous. They're called next, whatever, but we're going to call them C for current, P for previous. Okay. So when we find what we're looking for, okay, we're going to C points to the node that's going to be deleted, but I'm going to have to set P link equal to C link. Okay. So this is now going to point to where this points, okay, which is going to delete that node. Okay, so that's what we want. Okay. And then if that turns out not to be what we're looking for, okay, so if we're looking for 25 instead, we're first going to move C to point to this one, and P points to that one. So every time we move C up, we move P up. So in the initial configuration, we check the root, we move C. Every other time we move C and P as we go along. Okay. And we'll see that in a lot of things we'll need to do. Okay. Then when it comes to, once we're ready on the deletion, okay, once you're pointing to the node that you want to delete, again, let's say if we're back to this situation, well, let's think about it. We have again, different cases. Okay, so if we're trying to delete 5, okay, so in that case, both C and P would point to the root node. Okay, so to delete the root, pretty straightforward. We can just say root is equal to root link. Okay, so root is going to go to there. We've deleted the first one. Okay, simple enough to do. Okay, if you're going to delete one in the middle, again, it's what we just saw with the previous and the current. If you're deleting one at the end, you also need the previous and current. And that wouldn't make any difference really, because if P points here and C points there, okay, then we can still let P link be equal to C link, because C link is equal to null. Still going to take care of it. Okay. So that's what deletion would look like. Okay. You can do other things like print. Print, you'll just need one pointer. You're going to go through every time. Okay. And use just the C pointer to get from one to the other. Search is going to do something similar to that. I'm going to do my example a sum function. If they're integers, you can sum them all. Okay. So that's the basic idea behind linked lists. Okay. That's you can do a lot with them, but that's what we're talking about in general. Okay. So let's see here. Stop the share, leave on this one. Okay. Okay. So now let's share some code here in the terminal. Okay. So I'm currently on my Linux server. I'm in the week 2 folder. Okay. I already have this linked list file to start with. Okay. So we have some basic information to get us going. Okay. So here I've got, the first thing I have to do is create my struct. Okay. And then once I create my struct, I'll be able to start in with the class itself. Okay. Okay, so let's add our struct first. Get the right thing here. Okay, I'm showing my screen. Okay, so this comes, again, I've got the include IOStream and the using namespace standard just because we're going to test in the same file. We don't have to. We could just save this as a .h file or whatever and include it in another test program. Either way you want to do it is okay with me. Okay. So we have the keyword struct to create our struct. I'm going to call it a node. And then just list whatever it has. So it has an int for info. Again, int could be anything, or it could be a templated type, whatever you want to do. Okay. But you will have a node star link. Okay. So that's going to get us started there. That's actually not the end of that. That's the end of the node struct. Okay, I can then start my class linked list. Okay, and typically, again, I would put in private first. So this part is part of our normal thing for a class of our public. Okay, you could put in your accessor, mutator, all those comments if you want, but in this case, it's not going to make a lot of sense because data structures are weird. Okay, this is not a normal class we're creating. Okay, so now we're going to say this is going to end the linked list class. Okay. So again, the basic thing we're doing here is going to be a pointer to a node called root. Okay, that's what we're storing. Okay, that's what it knows. So that's a private function. Okay, and then we can start worrying about how we're going to put this together. Okay, so we'll start with our constructor so we can test it to make sure this part's working, which will just be linked list. Okay, and in our constructor, we're just going to set root equal to null. Null's in all caps. Okay, that's all we've got there. And then in our main, we should be able to say linked list LL, and that should get us going. Okay, so let's take a look at this. Compile this. If this isn't working, nothing else is going to work either. Okay, so we're good. Didn't do anything, but we're good. Okay, so the next thing we want to do, we want to be able to add something to our linked list. Okay, so I'm going to do an insert node, okay, which is going to take some data that we want to save. Okay, this is really you could also call this an insert tail because that's really what it's doing, but I'm just going to call it insert node. Okay, so I have to create a new node, okay, a new pointer to a node. Okay, so I'm going to say node, new node. This is a pointer to a node called new node. Okay, I have to further say equals node, new node, to allocate the memory. Okay, so if I just put the semicolon here, I'm not allocating the memory. I'm now allocating the memory for a new node. Okay, so now new node's a thing. So I can set, so since it's a node, I have info and I have a link. So I can set the new node data, okay, sorry, info is equal to data. Okay, and I can also set new node link equal to null. Okay, that's all we need to do is set this up. Okay, that gets us started. We have our new node now. Okay, now we have to check to see to the insert our cases. So if our root is equal to null, okay, it means we have no need to traverse anything. All we can do is set root equal to the new node. There were no nodes before. Now we have our new node. Then do a return. Okay, it's all set up. That's a simple case. There was nothing there. We create a new node, give it memory. Root currently points to nothing, to null. It's going to point to our new node now. And we're done. That's all we have to worry about. Okay. So once we've done that, we're going to return because we don't care about the rest of it. So if I make it to this point, it means that root was not equal to null. Okay. So right here, root, find your home keys. Root is not null. Okay. I could have done an if else, whatever, but if I'm done, let's return and be done with it. Okay. So that's what I'm doing in the line above. Okay. So here, I'm going to set a temp pointer. We talked about on the whiteboard. Okay. I'm going to set temp equal to root. Okay. So pictorially now we have at least one node. Root points to that one node. If we didn't have one node, we'd already be gone. Okay, so we have one node. Root points to that node. And now temp also points to that same node. Okay, they're both node pointers. Okay, so we now have to go through and find, we want temp to point to the last node. We know it's the last node because its link should be equal to null. If it's not the last node, the link should be to the next node. Okay, so we're going to traverse this. Okay, so we're going to start here by saying while temp link is not equal to null. If it's equal to null on the first one, we're done. Okay, if there's only one item, we're out of there. Okay, so if this is the case, we're going to let temp equal to temp link. Okay, that's going to move us on down the line. Okay, so what we're doing here basically is we're traversing the linked list, find the last node. Okay, so when we're here, we know we are at the last node. Okay, so once we're at temp, so I can say temp points to, it's a better, more accurate way of saying it. Okay, so we're now pointing to the last node in our linked list. Okay, no matter how many we went through to get there. So all we have to do to add this to the end is let temp link equal to the new node pointer. Okay, that's it. We're done. We've added one. Okay, so we can now test this to see if this works. Okay, we have our linked list. So I can now say ll.insert node. It wants an int. Okay, so I can do a 5. Okay, see if that works. Doesn't like something. Oh, I didn't do it correctly. Where's that at? Oh, right. A typo there. Got that. Okay. Okay. If I run it, really shouldn't do anything, but we can run it just to see. Sometimes you're going to get, actually, it's worth running at this point because it's very common in data structures, you're going to get a segmentation fault. A segmentation fault is when you try to access memory that you don't have the rights to access. Okay. Memory out of bounds error kind of. We'll talk more about segmentation faults and what to do about them later. But for now, we'll just know that that's a thing that could happen. Okay. And that's what it means. Okay, so we've got that working, but it doesn't do anything, so that's fine. So the next thing I'm going to go ahead and add, just makes it useful to work with things, okay, is going to be a print function. Okay, so I'm just going to call, it's going to be a void function called print list. Just call it print too if you want. I'm going to call it print list. Doesn't matter. Okay, so similarly, as we did before, I'm going to set up a temp pointer. Okay. And I'm going to, I can go ahead and in one step if I want, set it equal to root. Do it in 2 steps, doesn't matter. Okay. Once I have that, I can just say if root is equal to null, could be. If it is, there's nothing to print. So I can just see out that list is empty. Okay, that's all we have to do there. Okay. If not, okay, so do an else. We're going to traverse the list again. So I'm going to say while temp is not equal to null. Okay. So if temp's null, then we're just going to stop. Okay. In fact, I don't need to have an else there because if temp's null, it's not going to get it into the while. So it doesn't really matter. Go either way. That should be fine though. Okay. So while temp is not equal to null, we still have something there. So we're going to see out temp info. And we're going to put just a blank space. Okay. So we're going to go through the list. Okay. We're going to print out whatever's there. And then we have to advance it forward. So we're going to let temp be equal to temp link. Okay. If you've got 3 items, you start off by pointing to item 1. Okay, item 1's a 5. You print the 5. That's a temp1.info. And then by saying temp equal temp link, you're going to move to the second node. Okay. If that node's empty, then you're out of the while loop and you're done. But if not, you're going to keep printing. Okay. So when we're done with that, then we're going to have a C out here for an inline just to make it look nicer. Okay. And that's it. Okay. That should take care of it. We're going to end that there. So now we should be able to come down to here. And we'll start, before we insert, start by saying ll.printlist, which should say that there's an empty list. We're going to add 1. I'm doing ll.printlist again. Again, whenever you're writing any class or anything at all, test every function at least once, including all versions of your constructors. Okay, we got that. So first time list is empty, which is correct. Then we get a 5. Okay, pretty good. So let's go ahead and add a couple more things here. Test a little further. It wasn't much of a test. We weren't having to do much traversing. Okay, so let's go ahead and add at least Okay. And the tab key will straighten it back up. Let's do 15. Let's do 25. Okay. See if this works. There you go. Okay. So let's do one more function just to show you kind of what you can do. Let's say you want to sum up the numbers. These are integers, should be able to add them together. Okay. So the idea here is we're going to visit each node and we're going to calculate a sum. So you should be thinking to yourself, that looks a whole lot like, or it feels a lot like the print function. Okay, similar things. In fact, I'm going to take my print function. I'm going to kill it with Control K. I'm going to yank it back from the dead. I'm going to yank it again. Okay, go here and change this to a sum list. Okay. So our sum list, we're also going to start like we did before. All that's the same. We can do this as well. If the list is empty, the list is empty. Okay. But before my while loop, I have to initialize a sum equal to 0. I could have done that at the beginning. Doesn't matter. Yeah, doesn't matter. But you could. Okay. So we're initializing our sum as to 0. We're going to traverse through. Okay, but we're not going to print anything. Okay. Instead, we're going to let sum plus equal temp info. And then go on to the next one. Okay. No need for this, but we do need to return a sum, which means that our return type up here needs to not be a void, needs to be an int. Okay. All those, yeah. Okay. So this is our function sum list. It's going to create a temporary pointer to a node. It's going to point to root, which is keeping our first element, the root, the address of our first element. Okay. If it's null, then we're just going to say the list is empty. That's fine. If not, we're going to set up a sum variable equal to 0. We're going to go through, as long as temp is not null, we're going to keep adding temp info to sum and then moving to the next one and then seeing if we're done. Okay. When we're done, we're going to return the sum. Okay. As a debugging technique, you can always add a print function in here. So I could do something like cout. I like to add something so I'll know to get rid of it. So just some random character string, like 3 octothorpes. Okay. Sum. Just to see what's happening. Okay. So when I call it, I can now say LL. Now I want to test the empty part as well. So let me go ahead and on the empty list say LL.SumList. Okay. So I should get 2 that say it's an empty list. It's LL.SumList down here. Okay. I'm not really doing much with it. This is returning a number that I'm ignoring, but it should print out that value. Okay. See if this works. Okay, so we get the list is empty, so that part worked. Okay. The first time we call it, the sum is 0 because there's nothing there. Okay. But then when we call it again, we get the sum being equal to 45. Okay, which is correct. Okay. So we can now go back and take out that line, easy to see because it's got all the octothorpes there. Okay, get rid of that test data. Okay, now we can go back into here. There's no reason to call this like this. Okay, in fact, we know that works. I'm not going to worry about it. I'm not going to call it all. But down here, I'm going to cout sum is like that. And I'm going to go ahead and separate that with a new line character. Okay, so it should have that. Okay, so we have, I need an indel. That's ugly. Control V goes down a page at a time if you want to do that. Nope, now I went too far. Nope, I didn't go too far. It's right here. list is empty the first time, then we print out the elements of the list, it's fine, and then the list is 45. Okay. So that's the basics of creating a linked list. Okay, so if you have questions, let me know. But if not, work on some examples, I think will be the next step. We need to implement more functions. I'm gonna leave that as an exercise to the listener, okay?